Okay, so I want to take a minute and talk about how this recursion works because it's actually super brilliant. Okay, super, super, super brilliant. I'm not going to do 9 choose 4 because it's 500 operations. I'll try instead like, I don't know, like 4 choose 2. That might still even be a ton. So let's just do it by hand first. So like if I had A, B, C, and D, the question is how many groups can I come up with? So there would be like AB, AC, AD, and then BC, BD, and then CD. So it should be 6. So NChooseK, how do they usually do it? They'll like write it like this. 4 choose 2 is 6? Yeah, 6. Okay. So I'm going to use this recursive definition and show you kind of what this ends up looking like. It's kind of insane. Okay, so first of all, I'm going to have 4 choose 2. Okay, so 4 choose 2 is going to be equal to n minus 1, k minus 1. So 3 choose 1 plus 3 choose 2, because the k stays the same on the second time. So you decrease both of them here, and then you keep this number and keep this number. So that's how that kind of works. And choose 3 choose 2. Okay, so we only quit when either both of the numbers are the same or the bottom number is 0, which isn't happening right now. Okay, I feel like I'm going to need to stretch this out a whole lot. Well, I guess I'll do it when I get there. So 3 choose 1 is going to then go into 2 choose 0, and then plus, and then the 2 stays on the top, and then this number goes right here, 2 choose 1. You're starting to see how this is going to get super bad, super fast. All right, so this, gotta feel like a better way to do this. Chirps, chirps. And then this one becomes, let's see, the 3 and the 2 both get decreased by 1, so that's 2 and 1. Plus the 2 stays the same, and then the number on the bottom stays the same. 2 choose 2. Okay, so if you're forgetting what I'm doing, I wouldn't blame you because it's weird. Each time I'm running through it on the different iterations, whatever this is, the first one is I decrease both of them. And then on the second one, I decrease the top one, but not the second one. The top one, but not the bottom one. And anytime the bottom number is 0 or these two numbers are the same thing, then I quit. All right, so I do have that now. So we'll just do it this way. So what I have right here is 2 choose 0. That's a 0, so that's going to return a 1. Okay, so I know that that's 1. Okay, but then I go to the 2 choose 1. Again, those are not equal. The bottom number isn't 0, so I have to do this again. So I reduce them both by 1, and I get 1 and 0. And then I get 1 and 1. All right, those actually do both stop. So I go 1 plus 1. Okay, so all of those are sorted out. Now, this is all kinds of amazing. Now 2 choose 1, that's actually the same thing I had, but of course I don't know that because this is a recursive function, not paying attention to what the other branches are doing. But I have 2 choose 2. Those two are equal, so that's a 1. But I still have to explore further the 2 choose 1 branch. So it's 2 choose 1 goes to 1 choose 0 and 1 choose 1. And then since this is 0, this is 1, and since these two are equal, that's 1. So if I count all the 1s, I'm going to get the answer is 6, which is correct, but seems far more complicated than strictly necessary. However, there is a reason for this. Okay, so let me show you. So first of all, think about the order in which this happens. So if I'm trying to do 4 choose 2, so 4 choose 2 would be like, say, an open recursive call. So then I'm going to call 3 choose 1. Now I won't even have gotten to the 3 choose 2 yet because I have to finish 3 choose 1. So when I try to finish 3 choose 1, I go here. Oh, look, it finishes. Yay. I've got 1 and I've got this new one. So over somewhere in, I want to say memory, but this part of this thing has returned a 1. And I'm over here now still on this 2. Then I come over here, it returns a 1. Then I come over here and it returns a 1. So first of all, the first one returned a 1. Then the second one returned a 1. So that got added together and returned a 2. This 2 ends up getting sent over here and added to this 1, and then this becomes a 3. Okay, by the time I get back up to this 3 here, all these recursive calls have closed. So I'm going to try and highlight them in the order in which they're opened and shut. So first of all, we open 4, choose 2. Then we open 3, choose 1, which opens 2, choose 0. But then that, hold on, I did that funny. Open 4, choose 2, which opens 3, choose 1. That opens 2, choose 0, but since it gets to a finish line, it shuts down. So then it comes back with a 1 and it's happy. Then it opens 2, choose 1, which stays open. It opens 1, choose 0. This is hard to say. It opens 1, choose 0, which closes, and then 1, choose 1, which closes, and then it closes that one, and then it finally comes up and closes that one. So I've already got the answer to the first part. The answer to the first part's 3. Okay, now I got to do this again because now it's going to open up the second. So I still have this 4, choose 2 open. So I still have at least one open recursive call. So 3, choose 2 opens 2, choose 1, which then opens 1, choose 0, which has an answer and then closes. Then it sends a little 1 back. And then I have 1, choose 1, which opens, sends a 1 back. So I have 1 plus 1 gives me 2. And then this closes. Then I run 2 plus 2, or 2 choose 2, which gives me a 1. So that closes. I have 2 plus 1 is 3. So then this closes. And then I'll do 3 plus 3 is 6. And then the 4 choose 2 closes. So what makes this interesting is at various points in this process, you might have like a decent number of, like I think at one point we had this one and this one, all open at the same time. So you had 4 open recursive calls, but that's actually not nearly as bad as when we were doing recursion with factorial, where I think we got to like 69,987 or something like that, or 89 maybe, recursive calls. And this actually doesn't get, I mean, you can get too many recursive calls, but it's actually shutting them down pretty quickly. But another really interesting phenomenon of this in particular is that we're only adding 1s. We're starting an answer of basically 0, and we just keep adding 1 plus 1 plus 1 plus 1 plus 1 until we get to 6, which is actually not the same thing as we're getting from our other formulation. So if you look at this formulation right here, you're actually dividing by something, and you want to say you may or may not be getting something that is even an integer. So you're introducing opportunities for error here. Here you're definitely introducing opportunities for problems whenever this number and factorial gets really, really, really big. And you're doing division. So again, bad things can happen. So from a reliability perspective, this is actually a pretty reliable method because you're not introducing any error due to large numbers or any error due to division, but you are potentially introducing issues with having too many recursive calls open. And so that's the kind of stuff that we're going to see when we actually test using these 3 different methods on different types of inputs.